So the first type of problem asks us to compare the boiling points of pure substances. So on one side, since it's a pure substance, I'm going to do SO2 by itself. And on the other side, I'm going to do CO2. Now, when we're talking about boiling points, we're talking about breaking the intermolecular forces. The forces holding all the CO2s together and the forces holding all the SO2s together. Okay? And anytime we do a problem like this, we're going to draw the Lewis structure, okay, and we end up with this molecule that has resonance that looks like that. I'm not going to draw the outer electron pairs, although they're there, and I encourage you to please draw them. So the dipoles are going to move like this. So what we're going to get is CO2 that has a partially positive there and a partially negative there. And that's going to form a dipole-dipole interaction with the CO2 that looks like this. Okay. The shape of the water molecule is a linear molecule that looks like this. That means that although there is a dipole here, those cancel out. And we do not show those dipoles in the drawing. You can draw them wherever you want. And that's got a weak London force there. So for the answer, SO2 has a higher, I'm going to abbreviate boiling point BP, because SO2 exhibits dipole IMFs, which are stronger than CO2's London dispersion IMFs. Now, conversely, and we didn't make a big stink about this, but CO2 is going to have a higher vapor pressure, which means because it's got a lower boiling point, it's easier to make it a gas. Therefore, it's going to exhibit or emit more vapor at the same temperature as CO2, yielding what we call as a higher vapor pressure. Okay. Second type of problem would be when we have tie-breaking comparisons. Okay, so we got to remember that dipole-dipole bonds, which are the strongest, can be really strong when you have hydrogen in a dipole-dipole bond with oxygen, hydrogen in a dipole-dipole bond with nitrogen, or hydrogen in a dipole-dipole bond with F. Okay. London forces get to be really strong when the electron clouds are more polarizable, so when they're bigger. So we're going to be looking for hydrogen bonding as the first way of breaking a tie, and if we can't, we're going to look at polarizability of those electron clouds. Okay. So let's first off just compare these two guys first. Let's do the same thing we did there. In this case, I'm just going to jump right to the Lewis structures. These are both polar molecules with a partially positive there. And that's going to be a dipole-dipole bond with that partially negative N right there. Okay. And we're going to have a very similar thing here. Both of these molecules, I should put my lone pairs there, I'm sorry. Both of these molecules are trigonal pyramidal, 105-degree bond angles happening. They're in 3D. Which leads to dipoles that do not cancel, hence the dipole-dipole bond. Okay. Now these are both polar. Okay, so on first glance, we got a tie-breaking comparison because they're both polar. They both have dipole-dipole intermolecular forces. Well, which one has a higher boiling point? If you notice there, that is a type of dipole-dipole bond called a hydrogen bond. Okay, so although they both have dipole-dipole bonding, NH3 has a higher boiling point because it exhibits hydrogen bonding. And I'm just going to let you write this one out. Okay, let's now look at comparing the boiling points of HCl and HBr. Okay, so in this one, we have a polar molecule, partially negative, partially positive, forming a dipole head to tail with the partially positive, partially negative. It's really important that you guys leave the dipoles on your molecule if it's polar. Okay, that's a rule that I'm a big stickler about. Okay. Now, the same thing here before, both of these molecules are dipole-dipole. So we have to break a tie. How are we going to break the tie in this case? Now, there is not hydrogen bonding. If you look at there, that is not a hydrogen bond, and either is that. That's not a hydrogen bond. So what's the other tiebreaker? That's going to be the polarizability of the electron clouds. So because Br is a bigger atom than Cl, its electron clouds are more polarizable. Thus, HBr has a higher boiling point, even though they're both polar. Okay, now let's look at CCl4 and CBr4. Okay, so although that is partially negative and that is partially positive, they all cancel out. So in this case, we have a true London force right there. And same thing here with CBr4. Although that is partially negative and that is partially positive, they do cancel out. So we have a true London force between these three-dimensional tetrahedral molecules. Okay, so they both have London dispersion forces. You would assume they both have very similar boiling points. Okay, but in this case, the boiling point of CBr4 is higher for the same reason that the boiling point here is higher. We can't use hydrogen bonding as our tiebreaker, so we got to use size. And with respect to size, you need to say that the electron clouds in Br are more polarizable than the electron clouds in Cl, yielding a higher boiling point for CBr4. Now we're going to go to a situation that would not make sense. So let's look at a discrepancy here. So we have HCl and we have Br2. Okay, so HCl, partially negative, partially positive. HCl, partially negative, partially positive. And then we have Br, which is extremely nonpolar. So on first glance, you would say HCl has a much higher boiling point, okay? Because it's got dipole-dipole forces, which we know are holding the HCl molecules together more tightly as compared to Br2, which has only London dispersion forces. But here's our discrepancy. HCl ends up having a lower boiling point, meaning it's harder to heat Br2, okay? So a discrepancy is always going to be explained using size or electron clouds. So the reason must be that this London force here is much stronger than this dipole-dipole force because Br2 is such a large atom and has such polarizable electron clouds. Okay, last one. Describe what happens when water, okay, so we know that water is this. Ammonia and hexane. I'm just going to do C6H14 for hexane, okay? But it's nonpolar, we know, because it's only got those CHs, and we know that that's a nonpolar bond. So there's no dipoles there. So what's going to happen? Well, when you mix them, all the magnetic action is going to happen. So if we put them in like this box here, okay, water can form a ton of hydrogen bonds. So we're going to get the water, which is partially negative and partially positive, connecting with itself, but then it's also going to connect here with the ammonia. And that's a little hydrogen bond. And you're going to get other, like here you might have an oxygen hanging off there, nitrogen hanging off there, but then you're going to have the hexanes not connected at all. So I like to just separate those. So we have London dispersion interactions between the hexanes, and we have dipole-dipole forces between those. Usually something that has weaker IMFs tends to be less dense because it's spread out. They're not tightly packed with one another.